In this presentation, I'll be explaining single phase, half bridge and full bridge inverters. Now coming to the introduction of inverters. Now let us see the definition of power electronics. That is, the power electronics involves the application of electronics on control and conversion of electric power. Control and conversion of electric power. And let us see the block diagram of a power electronic system as such, and we can see what is the role of inverters, where we require inverters or where the inverters are required. That will be clear here. Now this is a power electronic system in which the sources are the source can be either AC or DC source, AC voltage or DC voltage. That can be the source. And this is a power modulator. Then the power modulator, after that the motor is coming. The motor can be either DC or AC, and depending upon the type of the source and the type of the motor, the power modulator will be different. For example, if the source is DC and motor is an AC motor, induction motor, the role of power modulator is DC to AC converter. That is called the inverter. And if source is DC and if motor is DC, it is a DC to DC converter. The role of power modulator is a chopper. Now, if the source is AC and the motor is a DC, then the power modulator is an AC to DC converter, control rectifier. Therefore, depending upon the type of the source and the type of the motor, the role of the power modulator changes. Now, basically the power modulator that controls the power flow between the source and the motor, that can be controlled by this power modulator. And the components in the power modulator, of course, that consists of switches will be there. The power electronic switches will be there, like MOSFETs or IGBT, or a semi-control switch like silicon control rectifier, then uncontrolled switch like diode, then energy storing device like inductance, capacitance, and energy dissipating element like resistor. Therefore, these are involved in the power modulator. And this is a control circuit in which that controls the power modulator. In order to control that one, we will have to sense either the position or the speed, that is sensed by using a sensing uniter, and that is compared with the reference value, and based upon that error, that is power modulator being controlled by that one. Anyway, power modulator is a device that controls the power flow between the source and the motor. For motor, that is the mechanical load is being coupled here. Therefore, where the inverter is required means inverter is required if the source is a DC source and if the motor is an AC motor, or there you need a DC to AC converter. That we call it, that is called as inverters. And of course, the control of the power modulator is done by using the control circuit that will be controlling the power flow between the DC source and AC motor. Therefore, there we requires inverters. Now continuing the inverters, as I told you, inverter is a DC to AC converter. The source is an AC. You can have a fixed AC to variable AC, fixed DC to variable AC voltage. For DC to AC converter, that's called the inverters. For the first classification is it can be either voltage source inverter VSI, or second it can be current source inverter CSI. Here I am going to explain the voltage source inverter. In voltage source inverter VSI, here in this presentation we'll be explaining single phase half bridge inverter as well as full bridge inverter. This is a topology of a single phase half bridge inverter in which there will be voltage source that is divided into two equal value, or the center tap is to be obtained, and these are the two switches S1 and S2. And of course, if the load is of inductive in natural RL load type, there will be a feedback diodes are required across the switch. These are S1 and S2 are the switches, and D1, D2 are the feedback diodes, and this is an RL load. Therefore, this is the topology of a single phase half bridge inverter. Now let us see the working of a single phase half bridge inverter, in which, as I told you, this is a circuit topology. The given DC voltage is divided into two equal values, so that we'll be getting a center tap like this point, that is marked as M here. And of course, these are the two switches S1 and S2. and you are connecting the load between this point P and M. The load is being connected, which is I'm considering it's an RL load. And here these are the feedback diodes D1 and D2 that is connected across each switch. And here when S1 is on, you'll be the conduction path is like this one. Through this one, you'll be getting a positive voltage at this point with respect to this one. And in this presentation, I'm considering that positive voltage means here positive with respect to this point. Then we call it a positive voltage. And if positive current means if the current is flowing in this direction, we are considering positive current. The reverse case, if here you are getting a positive, it will get negative voltage. And if the current direction is opposite, it's called the negative current. That is the assumption. Therefore, when switch S1 is on, then you'll be getting a positive voltage across the load. And similarly, if this uncontrolled device diode D1 is conducting also, you'll be getting a positive voltage. Therefore, either when S1 is conducting or D1 is conducting, you will be getting a positive voltage across the RL load. Here positive with respect to here. This is the center point. P will be positive with respect to here. When S2 or this diode D2 are conducting, one of them will be conducting. If then here you will be getting the voltage will become negative here with respect to this point. Then that we call it as a negative voltage. If either S2 or D2 conducts, here the point will become negative with respect to this point. Then you will be getting a negative voltage across the load because we are calculating the voltage of this point with respect to this one. Again, if depending upon the current polarity here, if the current is positive here, then for example, if you want to get a positive voltage here, a positive voltage is when S1 is on here. Similarly, when S2 is on, you will be getting a negative voltage like that one. And depending upon the RL load, the current will become, this is the shape of the current is this one. This is the shape of the current that is flowing through the load. Therefore, there are certain duration, for example, from here 0 to T1, you can see that when the current is negative, because the current is opposite here, at the same time, the voltage is positive from 0 to T1. Meaning that current is negative means that and voltage is positive means D1 has to conduct. Then only you'll be getting a positive voltage with a negative current. Therefore, during this region, D1 will be conducting. That is, this D1 will be conducting. The second case, when voltage is positive as well as current is positive, that is, you will be getting a positive voltage with respect to here. Similarly, current is also positive. Then that is possible only when S1 is conducting or S1 is on here, that is S1 conduct, you will get a positive voltage and positive current at S1. That is this case. When S1 is on here, you are getting a positive voltage and positive current. That is the second here. That is S1 is conducting from T1 to T2. Again from here, when here the voltage is negative, you are getting a negative voltage here, negative with respect to here. The same time, you can see that current is positive. That is because this is happening because of an RL load. In the case of a resistive load, always that will be in phase to the current will be in phase to the voltage. That does not happen. But since the load is a RL load here, you can see that even though voltage is going negative, still the current is positive. That is because of the inductance in this RL load. Therefore, in this region from T1 to T0 to T1, T1 to T2, T2 to T3, we can see that one voltage is negative. The same time, current is also positive. Therefore, current is positive means current is in this direction. The same time, you can say that one here negative here. That is possible only when D2 is conducting. When D2 conducts here, the current, it can draw a current in this direction. The same time, you will be getting a negative voltage. Therefore, here, that is the region that D2 will be conducting. And again here, negative voltage and negative current. Therefore, the current is negative. The current is opposite to here. And voltage is minus with respect to here. That is possible when S2 is conducting. S1 can conduct only in this direction. Similarly, S2 can conduct only in this marked direction. Therefore, in fourth case here, from T3 to T4 here, we can see that one, when negative voltage as well as negative current happens, the S2 can conduct. When S2 is switched on here, it can have a negative current as well as negative voltage. Therefore, the different devices that are conducting in this case are, that is marked as in a table here, when a positive voltage and positive current S1 is conducting, when a positive voltage and negative current D1 is conducting, when a negative voltage and positive current D2 is conducting, when negative voltage and negative current S2 is conducting. Therefore, that is marked here. But depending upon the voltage polarity across the load as well as the current polarity, the device, one of the devices will be conducting S1, S2, D1, D2. This is the output voltage that is available across the load, and this is the load current. Now, as I already explained the different modes of operation in the previous slide here, single phase half bridge inverter with an RL load. This is a RL load here. And as I told you, from 0 to T1 here, from 0 to T1, positive voltage and negative current. In that case, positive voltage and negative current means D1 has to conduct. Therefore, this is the equivalent circuit. When D1 conducts, the current will be negative, but the voltage will be getting a positive. The second mode he means from T1 to T2 here, you can see that T1 to T2, positive voltage and positive current. That is possible only when S1 is switched on. Here this is current will be like this one. Similarly, voltage plus and here minus. For that is the equivalent circuit is like this one. V by 2 is the voltage here, and here the voltage is equal to V by 2 when the S1 is switched on, and similarly the voltage is equal to minus V by 2. Therefore, this is the voltage and this is the current. And we can see that one, the voltage available here will be the V by 2 only. It's total voltage equal to V. That is a half bridge inverter, you will be getting only half the voltage. V by 2 here plus voltage and V by 2 equal to minus voltage. And this is the current through the load, and this is the voltage across the load. Therefore, this is the second mode here from T1 to T2, the switch S1 is conducting. And in this case, the feedback diode D1 is conducting. Mode 1, 0 to T1 mode 1. Therefore, that is again as a table it is shown the same thing. Continuing the single phase half bridge inverter with a RL load here. In mode 3, that is mode 3 is from here, T1, T2, T2 to T3. Here you can see that one, the voltage has been changed to negative, minus V by 2, but the current is positive. That's because of the inductance. Current is positive means current is in the same direction as this one, but you can have a negative voltage. That is possible only when this diode D2 conducts. Therefore, that is this equivalent circuit is this one. This is the equivalent circuit corresponding to mode 3. You will be getting a voltage equal to minus V by 2, but the current is positive. From, you can say that one, T2 to T3. When T3 to T4, the mode 4, here we can see that one, current is negative. The current through the RL load is negative. That is current means it is opposite. The current is in this section, and the voltage is also negative. Here negative with respect to here. That is possible only when here the current is negative here. This is a positive. I mean, this is the negative means current will be in this direction. Therefore, current is in this direction means that is possible only when S2 is switched on. When S2 is switched on, the current will be in this direction because this is the direct that indicates the direction of the current, and the current will be in this direction, and then you will be getting a negative voltage. Therefore, that is from T3 to T4. That's a mode 4 here. Therefore, here you can say again see that one here it is flowing like this one, and you will be getting a negative voltage plus minus here, and you are getting a negative current when the switch S2 conducts. Therefore, that is again shown as a table here. Therefore, in the half bridge configuration, even though the total source voltage is equal to V, we are dividing that voltage into V by 2 and V by 2. You will be getting the voltage, output voltage is an AC output voltage, either plus V by 2 or minus V by 2 is the voltage, and the current depends upon what the load you are conducting, RL load. If it is a purely resistive load, you will be getting an in-phase current, but that is if the inductance comes in that one, RL load, the current will be of this type, and depending upon the polarity of the current as well as the polarity of the voltage, one of the device will be conducting. And these diodes D1 and D2 are called the feedback diodes that provides feedbacking of the current that is required in the case of an inductive RL load as such. But if it's a purely resistive, theoretically speaking, no feedback diode is required. But since in the practical case, there will be an inductance. That is why you need a feedback diode across each switch so as to carry the reverse current. Now let us see single phase full bridge inverter. Single phase full bridge inverter, the difference is that the total voltage, that is V, is directly coming across the load as such, RL load. Now first we are considering a resistive load just to identify the why you require a feedback diodes. If you are considering a purely resistive load, but practically it's not possible, but just for an explanation I am explaining. If it is a purely resistive load, you can say that if the switches S1, this is S1, here it is marked as S1, S2. If the switches S1 and S2 are switched on here, you will be getting plus here, and of course here will be minus terminal. You will be getting the voltage plus V here, plus V voltage here. And when the switches S3 and S4 are switched on here, At the same time, the S1 and S2 switch off here. At that time, you will be getting here, you can say get here, there is on here negative voltage, and here, I mean, here you will be getting, when this and this is coming, here here positive and negative, here positive, and here will be negative, so that a negative voltage minus V comes across the R load. If it is a purely resistive case, you can see that current is in phase to the voltage. Of course, the magnitude is decided by V by R. That is the current magnitude. Of course, that will be in phase to the voltage. That is happening only if this is a purely resistive case. But practically, it won't be like that one. In that case, one of the switch S1, S2 will be conducting, or S3, S4 will be conducting. No need of feedback diodes. But in practical case, always there will be an inductor for this load. That is why we are considering an RL load as such. In that case, as I already explained, when S1 and S2 are switched on, you will be getting plus V. When S3 and S4 are switched on, you will be getting a minus V. Like that, voltage comes here. But the current through that one will not be in phase like that one, but the current shape is like that. This is shown as the current through the RL load. Therefore, there are instances during which you are in this, from example, again 0 to T1 period, you will be getting a positive voltage and you will be getting a negative current. It requires a negative current. Positive voltage means if plus and here minus, you are considering a positive voltage, plus here and minus here. And if current is in this direction, you are considering again positive current. Therefore, this is a positive voltage and the current direction represents a positive current. Now from 0 to T1, you can see that one, you are getting positive voltage and negative current. Positive voltage and negative current, what are the devices to be conducted? I mean, that's to be conducted. Therefore, from 0 to T1, the voltage is positive. The same time, the current through the load is equal to negative. That is, voltage positive and current is negative. In that case, the devices D1 and D2 conducts. Here, the devices D1 and D2, that is, this diode as well as this diode will be conducting. That is, path is like this one. Current is flowing like this one. Current is flowing in this path. And therefore, the current is negative. At the same time, this terminal is connected to this point, will be getting a positive voltage. Therefore, the devices that are conducting during this period, 0 to T1, are D1 and D2. That is D1 and D2. From T1 to T2, we can see that voltage is positive. At the same time, the current is also positive. From T1 to T2, current is positive. During this period, the S1 and S2 will be conducting. S1 and S2 will be conducting. In this direction it comes here, in this direction comes here, it comes here, different. Therefore, you will be getting a positive plus voltage here and a positive current. That is, here positive voltage and positive current. In that case, S1 and S2 will be conducting. S1 and S2 will be conducting. The third case here, from 0 T1, T2 to T3, negative voltage comes, that is minus voltage, negative comes here, and the current is also positive also. Negative voltage and positive current. Here, you can say that one, here negative voltage and positive current means D3 and D4 are conducting. D3 and D4 are conducting. You can say that one. Here, if it conducts like this one, you can say that current is positive. See, here when D3 and D4 are conducting, current is same direction, positive. The same time, here you are getting a negative with respect to this one, or your negative voltage is getting, but the current is positive. Therefore, from this point to this point, from T3 to T1, T2 to T3, there D1 and D3 and D4 are conducting. D3 and D4 are conducting, the third mode as such. The last one here, from T3 to T4 here, voltage is negative. Similarly, the current through the load is also negative. Therefore, current is negative here. Voltage is also negative here, minus with respect to this point. That happens when here the switches S3 and S4 are conducting. S3 and S4 are conducting. You can say that one. S3 is conducting. This path is like this one. Therefore, here you will be getting a negative voltage as well as the current is opposite. Therefore, negative voltage and negative current. So that is happening when S3 and S4 are conducting. Therefore, these are the four modes of operation depending upon the magnitude, the polarity of the voltage and the polarity of the current. Two devices will be conducting. Maybe the controlling switch, control switch like the S1, S2, S3, S4 for two, or maybe from uncontrolled switch like D1, D2, D3, D4. But always the magnitude of the output voltage will be plus V or minus V. Previously it was plus V by 2 and minus V by 2 for a half bridge. inverter. But here either it will be plus voltage V, this supply voltage, or it will be minus V. But the current will be it's not in phase because of the RL load. These diodes D1, D2, D3, D4, these are called the feedback diodes. That will be even though voltage, for example, if voltage is positive, you have to get a negative current. Therefore, that is why here the role of this D1 and D2 comes here. That is why D1 and D2 during that period. So these are called D1, D2, D3, D4 are called the feedback diodes. And of course, the switches S1, S2, S3, and S4 are called the control switches. I have already explained the different modes of operation, like mode 1, that is from 0 to T1, a positive voltage and a negative current, and then D1 and D2 are conducting positive voltage and negative current. D1 and D2 are conducting, and this is the corresponding equivalent circuit. That's D1 and D2 are conducting. Therefore, here you can say that current direction is opposite to the what we are considered as positive. Therefore, it's a negative. So the current is negative, and of course the voltage here, since it is connected to this terminal, is connected to the positive, it's a positive voltage. We are getting a positive voltage and negative current in the mode 1, 0 to T1 here. The second case, when T1 to T2, that's a positive voltage and positive current. The current across the RL load is positive. At the same time, the current through the RL load is also positive. That happens when S1 and S2 are conducting. That is, S1 and S2 are conducting. That is the corresponding equivalent circuit is this one. When S1 and S2 are conducting, the current direction is in this direction. At the same time, you are getting a positive voltage. For you are getting a positive voltage and positive current from course T1 to T2. That's a mode 2 operation. Now continuing mode 3 operation. Mode 3 operation means from T2 to T3. From during this time T2 to T3, of course, here you can see that voltage is negative. You have to get this is the inverter output voltage, that is negative. Voltage is negative. The same time the current is positive. Therefore, the current is in the same direction, but voltage polarity here plus and here minus. That will be obtaining when the diodes, uncontrolled, diodes like here D3 and D4 are conducting. When D3 and D4 are conducting, when D3 and D4 conducts, you'll be getting a negative voltage and positive current. That is negative voltage and positive current. That is, this is the equivalent circuit as such. Here, diode D4, diode D3. The current is flowing in this direction. So the current polarity is same. It's a positive current. But since it is connected to the negative terminal, you are getting a negative voltage. So voltage is negative. The voltage across the load is minus V. Minus V. At the same time, the current is positive. That is the mode 3 from T2 to T3. When T3 to T4 here, so mode 4 here, negative current as well as negative voltage. For the negative, the voltage across the load equal to minus V. The same time the current is also minus. In that case, here the switches S3 and S4 are getting turned on. Therefore, here S3 and S4 are getting turned on. You can say that one. Corresponding equivalent circuit is this one. When S3 and S4 are getting turned on, this is the current direction, which is same as a positive current, and the voltage here plus, and here you can say that one. No, this current is opposite, because this current is negative, because what we are considering positive current is opposite. Therefore, current is negative. At the same time, the voltage is also negative. Here you are getting plus and here getting minus, means it is opposite what we consider as positive voltage. For here plus and here minus means it is negative voltage, and here getting the current is in this direction means negative current. You are getting a negative voltage minus V as well as negative current through the RL load. That is corresponding to the mode 4, that is T3 to T4. That is obtaining when the switches S3 and S4 of the, that is switches S3 and S4 are getting turned on, you will be getting a negative voltage plus here and minus here, and a negative current. In this direction the current happens. Therefore, that is the fourth mode of operation, and this is called a single phase full bridge inverter, in which you will be getting either plus V or minus V, and the half bridge inverter you are being getting plus V by 2 or minus V by 2. And in the next presentation we will be analyzing these waveforms of the single phase, half bridge and full bridge inverter output voltage.